Go ahead.
So hello everybody. So welcome to the 24th time reworked the seminar. And today we are very happy to have Miguel Vanvlasselaer from Barcelona. He has done a lot of work on let's say bubble dynamics and also documented production from first order phase transitions. Yeah, please go ahead, Miguel.
Well, thank you very much for the invitation and the introduction. I'm very happy because actually I will talk about stuff that I did a long time ago, but that I love very much because it was the beginning of my research, so my PhD. So let me, yes, talk about the production of particles from expanding bubble walls, which come after tunneling. Okay, so let me, since I guess you know most of the basics, I will go very fast on phase transitions. Just we know, okay, QFT, there can be a landscape of minima. This can lead to transition among those minima, especially if you are in a plasma, like in the early universe, because we have this new, by the way, good question. Do you see the cursor if I move? That can help.
Yes, we can see it.
You can see it, right?
Yeah.
So I can
Yes.
play with it. Good. So you have this thermal correction, which is temperature dependent, and that will deform the potential as a function of the temperature. So typically at high temperature, you expect the origin to be stabilized by these temperature corrections. And then at low temperature, if you expect symmetry breaking, then you have the new minimum, symmetry breaking minimum that becomes favorable. And then if you have a barrier between the two minima, you have the typical first order phase transition that we are interested in. And then, so the mechanic or the technology to describe those transitions is essentially stochastic, right? You can compute the probability per unit of volume to have one of those bubbles that nucleates somewhere, and then it's essentially this tunneling from the origin to the broken minimum. And okay, so when you just after the nucleation, you have essentially for a little bubble two contributions that will matter in the energy budget. One, which is the energy from the volume, which drives the bubble want to expand to convert more and more of the volume to the new minimum, which is deeper. So this energy pushes the bubble to expand. And on the other end, you have the surface tension. So when you want to create an interface between two different medium, you have a tension that comes with this, and this costs you energy. And this tension comes like the surface of the bubble. So when you equate those two energies, you obtain a critical radius, such that if the bubble is smaller than this critical radius, then it will essentially shrink and disappear. If it's a bit bigger, well, it can expand. And this is what we call the critical radius. And now in the early universe, we can have those stages of phase transition, and we say in a conventional way that a phase transition begins when we have one of those expanding bubble per Hubble volume, and we call this temperature the nucleation temperature of the transition. And now, okay, to describe those phase transition, we typically consider mostly 2 or 3 parameters. The two most important ones are the strength of the phase transition, so this alpha, which is essentially the ratio between the energy release, so if I go back, so this difference of energy with respect to the energy which is already in the plasma, so it's how much the transition dumps energy in the plasma of the early universe and perturb and disturb it. So if alpha is very large, it means that we are disturbing a lot the plasma. And the duration of the phase transition, which is essentially the time between this first nucleation and the moment when all the bubbles collided among each other and the transition essentially completed and all the universe is into the new phase. And we define this time as beta, which is this ratio of the Hubble expansion over this typical time scale that I have in mind. And typically this beta will scale like the inverse of the radius of the bubbles at collision, because a very fast transition is you have many little bubbles that collide, and they merge when they are still very small. And a very long phase transition that would last maybe almost as long as the Hubble would be one very big bubble that fills the full Hubble, or maybe two of them. So here, actually, if you want to see some nice simulations of those processes, numerical hydrodynamical simulations. You can go to this paper and they have videos. So here you have essentially the temperature field. So that's the nucleation, then expansion, then percolation and collision and percolation. And here you have the velocity field. And okay, so another way to see the same thing is that essentially you can track the field value as a function of the radius. So this is like I'm taking the bubble and I'm cutting through it. So this is the initial bounce solution. Then I release it, and essentially I see that my bubble starts to expand. And those oscillations that you see there are essentially the fact that the tunneling point is not necessarily exactly the minimum, but then when I'm tunneling here, the field will relax around the minimum by some oscillations that you see here. And this bubble expands, and you see that the wall is becoming sharper and sharper as the bubble accelerates. Okay, but so now what I'm interested in essentially are the phenomenological consequences of those phase transitions. And the basic one, in a sense, is the reason why the phase transitions came back to life recently is gravitational waves, because now we have some many proposed experiments like Einstein telescope, LISA, that will probe the background of gravitational waves, possibly coming from the early universe. And phase transitions are a potential strong emitter of gravitational waves, namely via three different mechanisms. So the first one is simply the bubble collision, which is the fact that if I go back here, you see that there is a lot of there is a lot of energy which is stored in the gradient, in the stress tensor here. And this energy is essentially released when the bubble collide among each other. And since this is very anisotropic, you can produce gravitational waves via this mechanism. The second thing is are the sound waves. So as the bubble expands, it moves the plasma around, it creates sound waves that will propagate in the plasma. And since those sound waves are coupled to the metric, well, essentially you also produce gravitational waves in this way. And finally, those sound waves, after some traveling some time, they will decay essentially via turbulent effect that can also source gravitational waves. And now for all those sources, we expect some type of power broken law signal. But what is interesting is that this power broken law signal is characterized by one typical frequency, which is related to the temperature of the phase transition, especially the temperature at the end of the percolation of the phase transition, which we call the reheating temperature. So in a sense, if we can manage to see one of those power spectrum in the observatories, then we can obtain at what time in the early universe there was a phase transition. And
sorry, Miguel.
Yes.
Is the reheating temperature basically the same as a temperature at the percolation?
Yes, yeah, that's
okay.
Well, it's no, because the temperature. So here I would say it's the temperature after the reheating, not after the percolation. The percolation is the moment when you have this criterion of some amount of volume that has been converted, but you want also the energy stored into the stress and so stored in the bubble to be released. So to me, the reheating temperature is really when you reach again the thermalized state after the phase transition.
I see.
At least in my understanding. And yes, the frequency will be controlled by the reheating temperature, not by the nucleation one or the percolation one. Okay, so that was one important aspect. But essentially, if we want to hope to see one of those strong signals, what we will need to have is a phase transition which is typically quite strong. That is intuitive. I want to dump a lot of energy in the plasma, and quite long, because the gravitational wave is cumulative in time. So if I have a source that emits during a long time, the gravitational wave power is larger. So I want large alpha and small beta. What is good news in a sense is that the kind of in many models, large alpha correlates with smaller betas. But then you can turn the question around and say, okay, let's imagine that I have a model that will induce a lot of gravitational waves. So it means that the phase transition will have a lot of impact on the early universe. And so it should change other things. It should have other impacts than purely gravitational waves. And that's now what I would like to go to. So one specific impact is the possible creation of primordial black holes. I mean, I'm sorry, because I just noticed that there have been many papers. I didn't update this slide, and there have been many papers, namely by Yan and also by Wanyuan, so a few days ago. But so essentially here the mechanism is the fact that if the nucleation is so slow, so beta is very small, order 10 or less, there can be some patches of the early universe that will go to the new vacuum later. And so they will be essentially heavier than the patches around. So those are the so-called late bloomers. And since they're heavier, the full patch can collapse to a PBH. I mean, today it's still a heavy topic to know the details of the production of primordial black holes. I think there was a paper from Ryosuke, Yan, and Gabriele saying that if you take into account the corrections from if you take into account the right gauge to compute the curvature perturbation, well, essentially the amount of black holes is negligible. But then when Yuan was saying, I think recently, that, okay, you can have some reheating histories after the phase transition that still can pump up the PBH abundance. But so this type of scenarios are studied a lot at the moment. Another thing which I think is very nice is the possibility to produce magnetic fields from FOPTs. And this is quite important because today there are hints for magnetic fields that exist at very large scales. So the main hints from those come from the Fermi-Lat observations of blazars. So I won't explain the full story because I'm not the best person to explain that. But essentially, those observations of blazars are hinting toward quite weak magnetic fields, so 10 to the minus 15 Gauss, but at very, very long correlation length, so order megaparsec, and specifically also inside in voids, so not so far away from any galaxy cluster. And this is quite weird because then there doesn't seem to be, we don't know today astrophysical mechanism to produce those magnetic fields. And so you would expect that possibly they could come from the early universe. And so it's today still a field to try to produce magnetic fields from the early universe that will fulfill this condition. And you can do that, for example, with a first order phase transition. Well, there was also an interesting paper recently saying that actually you can even do it maybe from the crossover of the electroweak phase transition, but it depends on how many dumbbells are actually appearing in the crossover of the electroweak phase transition. Okay, but now the topics that I will talk about in the presentation. So first, baryogenesis. Well, for baryogenesis, we know the basic history of electroweak baryogenesis, which occurs during the electroweak phase transition. So we have those quarks that would bounce on the electroweak bubble, and if the quarks, specifically the tops, couple in a CP violating way with the bubble wall, then you have a different abundance of left and right in front of the wall, and this different abundance of left and right will bias the spirons, and so the spirons will start to create in front of the wall some baryon number, some B plus L, that is then swallowed by the wall and so frozen out. So that is the basic story, but I will discuss a bit later some alternatives to this basic mechanism. So here I give you some references. And another thing I would like to present is, of course, if you have a very strong phase transition, it should also have some impact on the abundance of dark matter, because we know, of course, the mechanism of freeze out or freeze in. But if I have, for example, a phase transition that has a lot of supercooling, obviously this will dilute, because at the end of the phase transition, I'm injecting entropy, and so I will dilute the pre-existing dark matter abundance. In this field, we essentially contributed by, I wouldn't say discovering, but yes, let's say discovering mechanism that will produce dark matter by the interaction with the expanding bubble wall. And those are the two topics I want to present now. So first, in a sense, let me present you the basic mechanism, which is the production of heavy particles from interaction between the plasma and the bubble wall that I did. Actually, it was perhaps my first paper with my supervisor, Alex, 6 years ago. So let me explain you in a very toy model. So let me take one scalar field, phi, which is the field that will undergo the phase transition. And then I want two fermions, one that will be very light and that will be abundant in the plasma, and one very heavy field that at the moment of the transition should be so heavy that it has totally decayed. So it is exponentially suppressed and it is not part of the plasma anymore. And I couple the three via this type of portal. So a mixing between the heavy and the light. And of course, I give a mass to the heavy particle. And now I would like to know if during the phase transition, I could have a fluctuation from the light field, so the light eigenstate, chi, to the heavy ones. Obviously, if the wall is very smooth and very slow, this cannot happen because of, let me go to this. Of course, if I have no wall or if the wall is very, very smooth, well, conservation of momentum does not allow a light particle to fluctuate to a heavy one. But now, in the presence of the wall, if the wall is quite sharp, well, this basic rule is broken because what forbids this type of interaction is the conservation of momentum and energy. But the conservation of momentum and energy intuitively comes from the homogeneity of space, which is broken in the presence of a wall. So what you should do schematically is to now redo your Feynman rules, but by taking, when you go to Fourier space, by interpolating, well, not interpolating, but incorporating the wall profile, which is this phi here. And when you do that, you see exactly, of course, you recover the conservation of momentum along the perpendicular direction to the wall and along the energy, if I do that in the wall frame. But now the conservation of momentum along the z direction, which is broken by the presence of the wall, is also broken. So I'm allowed, in a sense, to violate the conservation of momentum by a quantity which is of order 1 over L. And now I have to check if this transition violates the conservation of momentum by this quantity. So what is delta Pz for this transition? Well, actually, where did I write this? So okay, let's do the computation. So I'm assuming that I have a very fast wall moving in the plasma. So here gamma is the boost factor from the wall frame to the plasma frame, and I go to the wall frame, and I take this thing to be much bigger than 1. So of course, the energy of the particles entering and their momentum is of order gamma times the nucleation temperature, which is much bigger than the temperature itself. And then I can apply my Feynman rules in the presence of the wall. So I just do Feynman rules and the wall, and I obtain this result, where delta Pz is essentially the difference between the energy of the particle outside and the particle inside. So between the initial state and the final state. And in the case of a large energy, I obtain this m squared, where m is essentially the mass of the heavy particle, divided by 2e. But now it means that if E is large, the energy of the incoming particles is large enough, I will be able to produce them, because if you remember, I'm allowed to violate the conservation of momentum by a quantity which is of order 1 over L. And as the wall accelerates, the energy increases, like gamma T. And so this delta Pz will go down and will finally reach this 1 over L criterion. And when this happens, so we put essentially, since all those computation depends heavily on the shape, the exact shape of the wall. To be conservative, we just put a theta function imposing this relation here with an equality. now we have a probability of emitting heavy eigenstates from the like eigenstate, and it scales like the mixing angle between the two squares, so where the mixing angle is just this, times this theta function that we put a bit by end to put ourselves in this regime of production, which we call, and actually there are several similar situations, namely in a neutrino going through matter, and people call that the non-adiabatic regime. But okay, so now the question is, we have those particles that are produced, when the wall becomes fast enough, we have those particles that are produced. And what you could ask is, what are the consequences, or what can I do out of those particles? So essentially, there are three main consequences that I would like to go through. The first one is the fact that there will be a pressure coming on a pressure acting on the wall from this production of particles, essentially because this delta pz, which is a violation of momentum from the point of view of particles, is exactly the fact that particles are stealing momentum to the wall itself. And so the wall feels that as a kick, which when you integrate over a full abundance of particles becomes a pressure. So this will be, if I have the time, I don't know, that will be difficult, but that will be the last topic of the presentation that I would like to go to. But there are two other interesting applications. The first one is that this can produce dark matter, and this will be able also to do baryogenesis in a way which is different from the usual electroweak baryogenesis. And let me start with this baryogenesis mechanism that we did a few years ago with Alex and Wanyin. And okay, I assume that you know the issue of baryogenesis, right? It's mostly an issue coming from inflation itself, because if we have inflation will wash out any initial conditions. But then if you wash out any initial condition, you expect to have exactly the same abundance of particles and antiparticles after the reheating, after inflation. But if you do that and you let the universe evolve, protons will annihilate with antiprotons, giving two gammas. And of course, this will freeze out at some point, but this will freeze out at a value which is way too small. Actually, way smaller than the observation by 10 orders of magnitude. So at this point, you would like to have a mechanism that will transform 1 out of 10 to the 10 anti-baryons into baryons, so that when this annihilation occurs, you still have the observed baryon abundance. And typically, okay, you could manufacture models that escape the Sakharov conditions, but a good way to know if you can find a mechanism for baryogenesis is to verify that your mechanism will satisfy the so-called Sakharov conditions, which are the three conditions. So first, you would want a solution which is a situation which is out of equilibrium in the plasma. So actually, we have obviously a situation which is out of equilibrium because we are emitting particles that are heavily out of equilibrium. We also want a CP violation in some processes. I will show you that actually this production of particles is very naturally CP violating. And finally, we'll want either B or L violation. And at the end, I will show how we can incorporate that in the model. So let me first go to the CP violation, how we can do that. Well, in the toy model that I showed before, you cannot. But let's now enlarge a bit the model. So I'm taking now the Higgs field into account, still the scalar field phi, which has the phase transition. Now I need two families of heavy particles and two families of light particles. So I have two chi's and two n that I couple in this way. This is just the generalization of the mixing I had before. And I will add a coupling to the standard model. And now you notice that on the top of in a sense, the three-level production of chi going to n, I have also some Feynman diagram. So I have chi fluctuating to, say, AB n1. Then I have a loop using this coupling of the standard model, and n2. If you recognize those type of diagrams, this is roughly the same story than leptogenesis by the decay of a particle, of a right-handed neutrino, for example. And then what you want to compute is the difference of the rate of the fluctuation from chi to n, and the rate of chi bar to n bar. And when you do this computation with the interference between the tree level and the loop level, what you obtain is this. First, it's non-zero, so we have CP violation if there is an imaginary part in the coupling. So this is why we need two families, because if I have two families, in this case, I have a phase that I cannot remove. So this will be imaginary. And I have a typical function that I can compute and which has actually exactly the same form than in leptogenesis, and which is given by this. So by enlarging a little bit the model and enforcing the fact that I have a phase in the couplings and coupling to the standard model, I have very easily a model that can induce a CP violation. Now, okay, so I have the two first Sakharov conditions. Let's go to see if I can build a model by adding some baryon number violation that I can add by n. So I could do, in principle, I can either go leptogenesis way by incorporating lepton violation. I think I will skip this part, but it is doable. Or I can go in the direction of incorporating a baryon number violation. And then this would be a baryogenesis way. So this is the two different those two different mechanisms. But let me explain the baryogenesis one as an alternative to the electroweak baryogenesis. So here is the model. I'm sorry, I'm changing a bit notation, but let me re-explain from the start. So now I'm taking the standard model. So you recognize Q, capital Q are the quarks of the standard model. And here on the top of the quark of the standard model, I will add three types of particles. First, I will add a capital B, which is a heavy vector-like particle, which will be the heavy particle that I will emit from the wall. So essentially, it's what I was calling N before. I'm sorry for the change of notation, but what I want to do is from this mixing, producing from, say, the bottom quark, a heavy B in the same type of fluctuation than what I explained before. So first, I need those heavy vector-like particles. Then second, I will want, because I want CP violation, I need, let me show you the diagram that I want to consider. I want the B that fluctuates to a capital B, but then I need further particles to have CP violation. And I add for that some diquark that couples in the following way to the bottom and the top, and some new massive Majorana. And the reason to incorporate this massive Majorana is that now I can write this term, which violates the baryon number by 2 units. And so now I have everything. I have the loop here from those couplings that induce CP violation. I have the B violation by 2 units thanks to the massive Majorana. And I have the production from the wall of bottom quarks fluctuating to those capital B. Of course, here in this case, maybe I forgot to mention, the phase transition that I'm considering is the electroweak phase transition. So this capital H is the Higgs undergoing what I assume to be a first order electroweak phase transition. The wall becomes very fast. So I need some model that allows me to have a very fast electroweak bubble wall, even if we know that it can be tough, but it's doable. And then I have this fluctuation, the CP violation coming from the loop, and then the B quark will decay back to the standard model by going through those cascades. And since I have the B number violation from this massive term, I will have some baryon violation. So this is what I was explaining in those lines. So the main requirement in this model is to have the fact that the wall becomes fast enough to produce those heavy Bs. We will see that all this heavy sector to escape the current bonds needs to be something like more than 2 TeV. So it means that my gamma, so the boost factor, which will start to produce the wall will start to produce the heavy particles if gamma is larger than the square of the mass of the B divided by the time the temperatures times the wave. So this essentially tells me that the wall velocity, the wall boost factor, has to be something like bigger than 100. And okay, so now yes.
Miguel, so how can we get so large gamma factor for the electric phase transition? You said it's doable, but Can you explain a little bit?
Okay, so what you need is a mild supercooling of the electroweak phase transition. So something you can have, for example, a two-step electroweak phase transition. In two-step electroweak phase transition, you always find some region of the parameter space that will be supercooled.
Yes.
And this region, since it's supercooled, I'll come back to later. Probably not. I will not have too much time for that, but I will come back later to how we can compute the terminal velocity. But with mild cooling, say if I have the nucleation temperature around 50 GeV, or let's say more 10 GeV, then gamma factor of order 100 is totally doable. Actually, yeah, we have done a paper. I'm not explaining it. I'm not presenting it in these slides, but we have one of those two-step phase transition, and we identify the region in which this mechanism is viable. The issue in that is that typically those regions will be tuned, because supercooling in most of the models, if you don't have a conformal symmetry, is a tuned region. So yes, you can say these models to be viable, you need a tuning in the parameter space that induce the phase transition. That's typical.
Okay, I see. Thanks.
That's a typical issue of having strong phase transitions. Okay, so now that I have this baryogenesis mechanism working, let me see if what are the constraints that come with it. So first, since I have baryon number violating by 2 units, I will have typically, so first, I don't have issues with proton decay. That would be an issue that would come with if I violate the baryon number by one unit, but here there is no proton decay. But there is NN bar oscillations that violate the baryon number by 2 units. We have checked that actually we escape the constraints that are today of this. So the mixing of NN bar, which is constrained today to be less than 10 to the minus 33 GeV. And this, we can easily do it if the only mixing between the heavy particles and the standard model are in the heaviest quarks. So this story that I'm telling, it only works if we consider the bottom and the tops. So it couldn't work to have, for example, up quark fluctuating to a big particle, because then first we'll have large NN bar oscillations, but we will also have FCNCs. So FCNCs are another typical constraint. In this model, FCNCs appear at one loop, so we also avoid them. And finally, if we want to avoid the collider constraint, so directly producing them at the LHC, well, we need this whole dark sector to be somewhat heavier than, as I was saying before, than 2 TeV. So yeah, the proposal is this one. I have this weird dark sector around 2 TeV that violates the baryon number, and that has those diquark. And then I have an electroweak phase transition with a fast wall. Maybe it's a bit a lot to swallow, but in a sense, it has still a virtue that, to my knowledge, it's one of the models that really can escape the EDM bonds that today are quite heavy on the electroweak phase transition. So many models of electroweak phase transitions are ruled out by EDM bonds. If you compute the EDM bonds for this model, well, we don't have any issue. We escape them by three orders of magnitude. So this model does not induce electron dipole moment. And okay, it has another virtue, which is also the one that it should be somehow detectable. Because if I have a phase transition that will induce ultra-relativistic bubble walls, it has to be a strong phase transition, and then it will induce maybe unavoidably a strong gravitational wave signal that we could see in LISA, for example. So it's a way to reconcile strong gravitational wave signal with electroweak baryogenesis and with EDMs, at the price of having to introduce yourself the baryon number. So because usually electroweak baryogenesis uses the standard model's variance, right? And also, this model works in a different that I was explaining before. So you need a fast wall for this model. Typically, electroweak baryogenesis will fail for fast walls. And the reason is that electroweak baryogenesis relies on the scattering of the tops. So the fact that they are reflected away. But if the wall is very fast, all the tops will enter. And so essentially, you don't have any reflection coefficient anymore. And so if you run, for example, the code for electroweak baryogenesis. So here I'm using the code of Giulio Barni, which is actually very nice. And you run it for different velocities. The yield will drop as the velocity goes to 1. So our proposal works in the opposite regime, right? So it's complementary in a sense. So here I wanted to do the same type of model, but by introducing some lepton number violation. I will skip it because, I mean, it's quite similar. But let me go to the conclusion, which is the conclusion of this part, which is, okay, so we can create heavy states from fast walls. We have seen that you can also very naturally induce a loop that will induce CP violation. The computation is very similar to the one in leptogenesis. So we have CP violation. And now if you add baryon number violation from the by end in a dark sector, which is at the order of 2 TeV, we can have electroweak baryogenesis, a new type of electroweak baryogenesis. Typically, this model doesn't have any EDM bonds and is quite observable by gravitational waves. But you pay the baryon number that you have to introduce by end. Okay, so let me now go to the other thing I wanted to present, which is the production of dark matter from those type of phase transition. So now let me, again, I start with a very toy model and I explain you the basics. So I will take 2 particles. So now I'm again changing totally the notation. I'm sorry, now it's H which undergoes the phase transition, and phi is heavy dark matter that you protect via some Z2 symmetry, and you give it a large mass. And what I would like to show is that as the H particle from the plasma crosses a wall that goes very fast, it can upscatter to 2 heavy dark matter, so 2 heavy phis. So essentially, when you implement this shift of H going to H plus the VEV as it goes across the wall, you get this trilinear coupling that is the coupling that could create so H to phi squared. But again, this transition would violate the conservation of momentum. So we go through exactly the same computation as before. We go in the wall frame, we compute the energy, we compute how much momentum we can steal from the wall, and we obtain at the end that the probability of creating 2 heavy particles from one light H is the following one. And again, this is kind of a mixing angle, and we have the theta, the heavy side theta that we put by n to put ourselves in this non-adiabatic regime. And now you can do the computation of having how much heavy particles, since those particles are stable, how much heavy particles are produced behind the wall. So it's just making an integral. You get the following type of answer. Here, the exponential is essentially coming from this heavy side theta after the integral. So it tells you that as you enter into the adiabatic regime, so you escape the non-adiabatic regime, the abundance produced by the wall becomes exponentially suppressed. So this is intuitive. And from this, you can compute today what is the remnant or the abundance of dark matter that you have. First, we see that we have a large prefactor. So this intuitively, this process could produce more dark matter than freeze out. But at the same time, it scales like the inverse of the mass. So as I will increase the mass of the dark matter, I will have less and less. And now we can ask, okay, in a parameter space for some type of phase transition, what is the region, what are the masses for which I can reproduce the observed abundance of dark matter? So those are what we show. This is what we show in those contour plots. So here I have a contour plot of lambda. So lambda is this coupling between the phase transition scalar field. So the H here can be either, again, the standard model Higgs having a strong FOPT, or a dark one. Both can work. So here, if the H is a dark Higgs, so a dark phase transition, the region that fulfills the observed abundance of dark matter is this triangle. So essentially here, the dominant contribution comes from usual freeze out. And on this upper edge, the dominant contribution comes from the bubble expansion, because we have always two contributions, because those heavy particles, they were thermalized in the early universe. So they froze out like any heavy particles. And at the end, you have two contributions, one coming from the wall, one coming from the freeze out. And then you wonder, okay, which one is the dominant contribution? If you have larger coupling, typically it is the bubble wall, because freeze out is more efficient with larger couplings, but the bubble wall production is more efficient. Sorry, it's the other way around. So freeze out eliminates more dark matter with larger couplings, and the bubble wall produces more dark matter with larger couplings. So at larger couplings, we have dominantly bubble expansion, and at smaller couplings, we have dominantly freeze out. And what you typically see is that you can reach very large masses, up to 10 to the 7 GeV. Here we consider a mild supercooling. And here is the same type of story if we consider that the Higgs is if we consider that the H is actually the Higgs boson. And here, all the solution is this contour that extends up to 10 to the 6 GeV. And again, okay, so this is assuming that the electroweak phase transition has a supercooling of order 30. So it would be a nucleation temperature close to 5 GeV. Okay, so something a little bit amusing that was discovered by Jan Filippo-Sala and Jason Baldes is the fact that there is a region of parameter space in which this dark matter produced by the bubble wall will be also warm dark matter. Well, this was important a few years ago because there were all those issues about dark matter at small scales. So namely those too big to fail. And so it seemed that there was less power at small scales. I'm not sure how much today this issue is resolved. So it depends a bit on who you ask. But the point is that if you have warm dark matter, typically you wash out a bit of power at small scales, and maybe you fit better some galactic observations. So that's why people wanted to play a bit with them. In general, in the field, people wanted to play with warm dark matter. And we wonder if our case, since we are emitting particles that are very fast, those heavy particles, those heavy dark matter can also be warm. And actually, there is a little region of parameter space in which it is, because, so let's do the computation. The average energy of the emitted dark matter is given by the mass squared over T nucleation. Then you have to redshift it to today. And actually, so to all those observations, they are matched at the velocity of the dark matter at the equivalent at the matter radiation equivalence time. And typically, what we call a warm dark matter is a dark matter for which the velocity at this equivalence is of order 5 times 10 to the minus 5. If you go warmer than that, you will encounter the Lyman alpha bounds. So you cannot go warmer than that. But if you go exactly at these sweet spots, you wash out enough to maybe relax some tensions with galactic observations. So we wanted to target this 5 times 10 to the minus 5 velocity. And we find that we can do that if we have some dark matter at 10 to the 8 GeV and a transition which occurs exactly at the scale of the electroweak phase transition. Okay, this I will probably skip because it's the same story, but with other type of secluded sector. If you have, let's say, now fermions or glue balls, and we made the same story, we also obtained that you can have a little region of the parameter space which has exactly warm dark matter with the temperature that we want. And okay, maybe how much time do I have? Something like 10 minutes, 15 minutes?
I think you still have 15 minutes
15
because we
minutes,
studied
okay.
a bit later. Yeah.
Because I wanted to finish on the problem of the wall velocity. Because in all those studies that I showed you before, one critical parameter is this boost factor from the wall to the plasma, which is essentially the velocity of the bubble wall, or the boost factor, that is. And now the question is, how would you compute this object? Well, if you are in a vacuum phase transition, it's very simple. The boost factor grows like the radius of the bubble. So the bubble essentially accelerates with gamma growing linearly with r, so almost linearly in time. So it means that at the collision, the gamma factor will be extremely large. Typically, it will be the Planck mass divided by the wave of the phase transition. So for the electroweak phase transition, that would be something like 10 to the 15, 10 to the 15 or so. But now in the plasma, you have the back reaction from all the particles that enter in the wall and interact with it. And you could have, in principle, a balance between the pressure from the plasma and the acceleration from the vacuum. And so that gives you essentially two regimes. So the first regime in which this pressure from the plasma does not manage to stop the acceleration, and then the wall runs away. So it accelerates until collision. Or you reach a terminal velocity, and then it becomes a problem quite complicated to find exactly what is this velocity. Well, people have done it for, actually, it was a very long work for sure, but now there is a code that allows you to solve for the velocity as long as the velocity is not too large. But here I would like to talk about what about the case in which the boost factor, the wall is already quite large? How can I know if the wall will actually run away or reach a terminal velocity at quite large gamma? So here actually I stole a few slides from Matthias Carosi. I would like to thank him for that. So typically, as a rule of the thumb, if a slide looks ugly, it's mine, and if it looks nice, it's from Matthias.
Okay.
So let me explain how the two different frameworks in which people have been working to compute this velocity. So in principle, what should be the most basic framework to compute the wall is to solve the equation of motion of the wall. So this equation of motion for the scalar field and the distribution for the particles in the plasma. Of course, the wall will itself deform or give kicks on the particles that will drive the particles away from equilibrium. So you need to solve for those distribution, and then you plug this back into the equation of motion of the wall, and you can solve this problem. It's very complicated. That's exactly what the code that I showed before is doing. And the opposite method, but not the opposite method, but in a simplified way to work in the regime of a fast wall, is this intuitive picture of having the fact that the wall is the velocity of the wall is a balance between this release of energy, which is delta V, a driving force, and all the pressure that the particles exert on the wall by first getting a mass or emitting particles. And so essentially this pressure from the plasma becomes now just a sum over all the type of transition that will give a kick on the wall. And then you sum over those different transitions and you integrate over the phase space and you get a pressure. And then you try to match the release, so the driving force, with this pressure from the kicks. That's what people call somehow the kick picture. What I would like to show, so I will first give you some of those contributions, but then I would like to show that those two reasoning were not matching at some point, and to correct, in a sense, this picture from the contributions we discovered in the kick picture. But okay, let me present you the three typical contributions that you will find in the kick picture for the pressure on the wall. So the basic one is just the fact that particles, as they enter into the wall, for example, you can think of the top, they will get a mass. So since in the whole frame, the energy is conserved, it's stationary. So here, this object, which is P perp plus PZ plus the mass squared, is a conserved quantity, but the mass changes across the whole. Let's say the top is massless and then becomes massive. Well, that means that to compensate for the energy to remain constant, the momentum has to decrease. So as the top enters in the wall, it feels a force that decelerates it. And this force is then transmitted to the wall as a kick. Then you can just compute first how much momentum the particle loses. You say, okay, this amount of momentum that the particle has lost is actually transmitted to the wall. So it's a kick, which is this difference of momentum that we compute, and it's in the limit of large energy. It is just the difference of the mass on both sides divided by 2 times the energy. At large velocity, all the particles will enter just because their mass is too small to stay outside. And then now I can go back to my kick formula. So essentially here I have 3 objects. So first I have the exchange of momentum. So how much momentum has been transferred from the plasma, from the particle to the wall. I have the distributions of the incoming particles, so which will just be the abundance of in this case of the top entering into the wall. And finally, the probability that the transition happens, which is in this simple case, just becoming 1, since all the tops are entering. I put everything together, I perform the integral, and I find this so-called Bodecker-Moore pressure for the particles getting a mass. And that's the first contribution. The second contribution, which has been which has been quite important to change our picture of phase transition, is the fact that as they enter into the wall, typically charged particle can emit any gauge boson that changes mass across the wall. So if I have, again, let's take a top. Since the Z gauge boson gets a mass on one side, well, this any particle that couples with the Z can emit massive Z particles that will induce also a kick on the wall. We know how to compute this. What matters in this case is that the exchange of momentum due to this this so-called transition radiation contribution scales like the mass of the gauge boson. So if I go back here, the exchange of momentum was scaling like 1 over the energy. So as the wall accelerates, it was decreasing the kick was decreasing, but what was increasing was the abundance. So at the end, the pressure due to the 1-to-1 particles getting a mass was constant in a boost factor. But here in the case of the emission of gauge boson, this kick is constant in velocity. So this induces that the pressure in itself is linear in the boost factor. This was important because since, as you remember, a runaway wall can reach a very large gamma, since this pressure, the contribution from this pressure also grows like gamma, it means that any phase transition that would have gauge boson that becoming massive will be ultimately stopped. So the runaway will turn into a terminal velocity because of those emissions of gauge bosons. Okay, there's been a little of controversy about what is the exact scaling. My understanding is that today it's stabilized to a linear scaling. And the third contribution is the one I was mentioning just before. If you emit heavy particles, so exactly in this light state emitting heavy states, again, we have an exchange of momentum, so we can run all this machinery of production. And then what we find at the end of the day is that there will be a pressure from this mixing that will turn on when gamma becomes large enough to enter in the non-adiabatic regime, and then saturate at a constant value.
Sorry for interrupting,
yes.
Miguel, so you have 5 minutes?
5 minutes.
Yeah.
Well, actually, it would be a nice place to wrap up, but I would still like to explain one thing. So here is just a slide explaining the three contributions. And I just wanted to say, okay, all this discussion about the contributions for the fast walls, you could say, okay, who cares if the wall is very fast or run away? That you would not see really the difference. But actually, you see the difference because in the case of a runaway regime, which is acceleration and cohesion, most of the energy of the phase transition will be stored into the gradient, so in the scalar field. And in the terminal velocity regime, most of the energy will go to the sound waves. And we expect, there is still also controversy about how you should compute the two contributions to the gravitational waves, but those two sources will give a spectrum which should be somehow different. So in principle, from observation, if you have good enough resolutions, we should be able to distinguish those two regimes. And so that's why we want reliable computations also in the relativistic regime. Okay, so I wanted, if I have 5 minutes, right? Okay,
Yeah.
let me go back to this point because at this level there was an issue, mostly coming from the people working in this type of framework. So if you solve these equations, so the equation of motion and the Boltzmann equations, people were not finding the contribution from particle production and from transition radiation. And so at this level, you could think that maybe since this method is in a sense more rigorous, maybe there is something deeply wrong in the kick picture, or in a sense, people didn't search well enough in the sets of equation. Maybe it was hiding somewhere in the Boltzmann equation and people missed it. Or actually there is a missing term in this set of equation. And this is exactly what was the goal of this paper with my collaborators. So when Johan, Matthias, Bjorn, and Carlos. So we wanted to reconcile the two formalism. And what we found is that actually in this in the equation of motion of the bubble wall, people had truncated one term that was exactly containing the particle production. So in a sense, by starting from first principle, we recovered this term and we put it back, and now the two approach agree in the regime of large velocities. Of course, I don't have the time to go through the detail of the computation, so let me skip all the basics that I wanted to explain. So I should have to explain you the in formalism and the CTP formalism and two particularly irreducible action. But in any case, I'm not the best person to explain that. So let me jump to the result. So we do a long computation. We restart from in a sense, what is the most generic formalism? Of course, so from this formalism, we can recover let me show you that. So in this formalism, we typically recover the equation of motion of the Higgs. But what we found is that if you in this CTP formalism, you had one more term that was containing all the two particle irreducible, so the two loop contributions, and people truncated back in time. They truncated away this term because it was a higher order term. But we see that by introducing it back in the equation of, so essentially this equation now becomes this more generic equation with a new term. Those two loops, let me show you this. It's a bit messy, showed like that. The two loop terms, when you compute the contribution from the third term in this here, recovers exactly the contribution from the emission of heavy particles. So actually we did the computation again. Let me go at the end. So we solved and we integrate the term, and we obtain exactly the pressure from the emission of every particles. And we saw that at large velocity, the two computations agree very well. So the computation from the kick picture and the computation from this more generic CTP formalism. And exactly the same will happen for the transition radiation. So we recover we do exactly the same computation, but with a more generic formalism, and we reconcile the two methods. I'm sorry, I was very fast on this work, but I find it important because it was two different communities working each of them with the different formalisms, and it was not agreeing. So now we reconcile them. So please, if you have any questions, I will stop here.
Okay, thank you, Miguel. Any question about this talk?
Hi, Miguel.
Hello.
Yeah, hello. Thanks for your very clear and organized talk, which I learned a lot from.
I wouldn't say very organized. It was very messy, but I wanted to show many things.
Yeah. Okay, I have very basic questions. So, when you consider the wall with a larger velocity, and you consider the modification of the Z components, the momentum transfer, since the low mass particle can transform to heavy particle.
Yes.
And I saw that you have some distribution function f. So is that distribution function is still the thermal equilibrium, the Boltzmann?
Okay, so let me come back to the. So in which computation do you because typically this f it would be f chi, right? It would be the distribution of the light particle, which is in equilibrium at the moment of the transition. Yes. So this.
Yeah. Okay.
By assumption, we assume this to be in thermal equilibrium during the transition.
But why this assumption is verified? Since if there is a very strong first order phase transition, if there is some reheating or in front of the wall, why we still using is a thermal equilibrium distribution for the momentum?
So if you have a heating due to the wall, so typically you describe that via hydrodynamics, right? So you say there is a compression wave in front of the wall with some temperature that you solve by hydrodynamic matching. But then, I mean, you just need, of course, you just need to use the distribution function, the thermal one, but with the temperature T plus, so the temperature that you obtain from hydrodynamic, which of course will be higher. But you need to, instead of putting the distribution at T nucleation, you put it at T plus. But in a case of a detonation, so where we are typically considering detonations, well, it's the hydrodynamical profile is first you have the wall, the plasma in front is at the T nucleation, and then you have a rarefaction wave. So it's a detonation. So the plasma in front of the wall is not heated in this case. So I think T nucleation is correct.
I see. So I see.
You could have corrections for hybrids and deflagrations.
So for cases, even if there is some reheating, so the particle interactions are still fast enough to be thermalized in that reheated temperature, right? So which means
yes, go
Miguel, I think you need to explain a little bit more about what is detonation. Probably he is not familiar with detonation.
Oh, okay. Sorry. So essentially, when you have a phase transition in those plasma of the early universe, there are three different static solutions. So at low velocities, so for a wall that propagates slower than the speed of sound, essentially, yes, you will be in front of the wall. You will have in front of the wall compression wave with a larger temperature in front of the wall. Then, okay, you have a region which is a bit more complicated, which is a hybrid region. But then as soon as the wall becomes fast enough, so the Higgs wall, it goes so fast that the plasma in front is not, the
not
information in the plasma goes too slowly so the plasma doesn't know that the wall is coming. So essentially it is the thermalized plasma at the moment of the nucleation. Then the wall hits the plasma, it compresses the plasma, and then you need a rarefaction wave to behind the phase transition, behind the phase boundary. But this is the type of profiles that we have in mind. So there is no heating in front of the wall just because the wall propagates too fast for the plasma to be to know that there is a wall coming to it.
I see. So even when the wall velocity is not very large, there is some part of reheating in front of the wall. Right?
If the wall, yes. If the wall is typically, if the wall is slower than what is the so-called Jouguet velocity, which will be order of a bit larger than the speed of sound, yes, the plasma will develop a compression wave in front of the wall.
Okay, thanks.
And this compression wave is indeed heated, yes.
Yeah, but most of Miguel's mechanism relies on fast bubbles, so it is already in the detonation region.
Exactly, yes. So yeah, I was only talking about detonations and runaway in this talk.
So which means for the detonation, in front of the wall, we're still using the nucleation temperature.
Exactly. So the plasma is unperturbed in front of the wall.
Okay. So I'm just curious, if there's some reheating inside the wall, which means even if it's in the broken phase, it is reheated. Is there a symmetry restoration in that small region? Which means if there's symmetry restoration, the spanner rate may be unsuppressed, which may be quite dangerous for the electroweak baryogenesis.
So about what mechanism do you have in mind? So you are talking about basic electroweak baryogenesis, right?
Yeah. Yes. Yeah, I realized since what you talk about is maybe not the standard electroweak baryogenesis.
Exactly. So that's what I was saying during the I have the slides here. We don't use the spherons, and actually what we have to do, we have to put by end a B violation. So that was in a sense the ugly part of this mechanism, which is that we are not using spherons. And the reason, it's exactly that. The spherons are only active in front of the wall. So, and all what we are doing, is in the broken phase where the spherons are inactive. So that's why we need B violation. A B-violating interaction. B-violating interaction.
Thank you. Yeah.
Electroweak baryogenesis will typically consider hybrids or deflagrations. Exactly for this reason. You need the TOPS particle to be able to diffuse in the symmetric phase where the spherons are active.
Yes. Okay, so are there more questions? So, are there more questions from the audience? Seems no. And if no, let's thank Miguel again. And thank you very much for this very nice talk, Miguel.
Thank you very much for the invitation. It was a bit intense those days, but I was happy to present.
Okay, and see you guys next time.
Ciao.
Ciao. Looking to stop.